Now, before calculators, regression lines were always done by hand by the formulas. So let's say we were talking about those distance and driving the golf clubs, and suppose somebody found this, let me fix the thing, to be the regression line. Well, it's shown here, and it kind of fits the data, but is it the best line? Now, with the calculators and technology, we know it's the best line. But if I was doing it by hand, how would I know how good it is? Well, we'd have to compare a prediction made with the line with the observed values and see how far off we are. Well, we call that difference a residual. The residual is the difference between the observed value and the predicted value. So in this case, we would have taken the observed y value minus the predicted y value and found that the residual for this example was 4.7 yards. So that's a prediction error in that case. Let's do another example of that. And by the way, you'll hear least squares line and regression line interchangeably. So don't get confused. Least squares is the regression line, and least squares is how it used to be done by hand. They would find the least residuals. It was a very complicated method. But so if you hear both of those terms, don't get confused. They really just mean the same thing. We just want to minimize the residuals, so we're doing the least residuals, so least squares of the residuals. Anyway, a student at Joliet Junior College conducted a survey of 20 randomly selected full-time students to determine the relation between the number of hours of video game playing and their grade point average. And she found that a linear relation existed between the two variables, and she found this equation to represent that relationship. Could we predict the grade point average of a student who plays video games 8 hours per week? Well, sure we could. To make a prediction using a regression line, all we're actually going to do is plug in our x value into this regression line. Remember, this y with a hat means this is our prediction for a y value. It's not the actual y value, it's just a prediction. So this equation was negative 0.0526 times x, so in this case that would be times 8, plus 2.8342. So we would put that in the calculator. Let's see, negative 0.0526 times 8 plus 2.8342. And we get 2.4134. So what this means, this is the predicted GPA for someone who plays video games 8 hours per week. Now let's review interpreting the slope and the y-intercept. What would it mean for this slope? So let's remember how we interpreted the slope. For each increase in hours per week, hours playing video games per week, the GPA, is it increasing or decreasing? Look at the slope. GPA decreases by 0.0526. I would be careful not to say that it decreases by negative, because then you're saying it actually increases. If you decrease by a negative, then you're actually increasing. Be careful there. Let's see if the Y-intercept makes sense. It's saying if your X value is 0, so if 0 hours per week are spent playing video games, the GPA will be 2.8342, which I don't think that makes sense. I think it would probably be higher than that, but we're going to go with it. Now let's say a student who plays video games 7 hours per week has a GPA of 2.68. What is the residual for a student who plays video games 7 hours per week? So to find the residual is found by taking the observed minus the predicted. You're finding the difference between what actually happened minus the observed. And let's be careful, that's the observed Y value minus the predicted Y value. If you did the X values, they'd be the same, 7 hours and 7 hours. That would not make sense. So I need to come off to the side and find the predicted Y value. So I'm just going to, instead of 8, we're going to replace that with a 7. So I can go in the calculator, and you can actually go up and select that, and then change the 8 to a 7. So my predicted value is 2.466. The observed was 2.68. So the residual is 2.68 minus 2.466. The residual is 0.214. That means our prediction is off by 0.214. That means the error in our prediction is 0.214. All right, let's practice some more. And I actually invite you to try some of these, and then you can come back and check your answers. So the American black bear is one of the 8 bear species in the world. It is the smallest North American bear and is the most common bear species. And they did a long-term study of the population in the Great Smoky Mountains. One aspect of the study was to develop a model that could be used to predict the bear's weight, since it's not practical to just walk up and ask a bear to get on a scale. And they thought that maybe the length or the height of the bear was related to its weight, because they could kind of measure their height. And so they did get 12 bears, and they got their height and their weight, and they thought maybe we can get an estimate on this. So which one is the explanatory variable based on the goals? Well, since they're trying to predict the weight, because we are predicting weight, the length is the explanatory variable. Whoops, I move it up. Because we're predicting the weight, the length is the explanatory variable. Then it asks us to determine the regression line. So I just want to remind us how we would do that. We would put this would be our X and this would be our Y. We'd put it in L1 and L2. So we can actually review a lot on this. So I'm going to go stat, clear out what was in there. Now I'm also going to review looking at the graph. So I'm going to go to Stat Plot, turn that on, press Zoom, and go down to Zoom Stat so I can look at the scatter plot. And I just wanted to look at that because it does look like there's a positive correlation and it does look fairly linear. Next, I'm going to double check that my mode, I have my stat diagnostics on. Now I'm going to press stat again, and I want to do the linear regression. And we're going to talk a lot about what all this means. This time, I think I want to store the equation because I want to look at it on my scatter plot. So to store the equation, I want to put it in Y1. So if you press alpha and then F4, that pulls up my Y variables and I can put it in Y1. So it's going to store the equation there. So if I go back to the graph, which I will do in a minute, it'll have that line already there. So I'm going to go ahead and write down the equation. A is going to be my slope, so this would be y equals 1.68 x minus 139.84, and it says r squared is 0.483 and R is 0.695. So let's remember what R is telling us. That is our correlation coefficient. And it's telling me the strength and the direction. So this tells me strength and direction. So since it's positive, we're in a positive direction, and 0.7 is pretty strong. So this would be a strong positive correlation. I think of it as that's about 70% of the data is fitting the pattern. It's not quite that, but I kind of think of it that way. Now, can we use this equation to predict the weight if the height is 155.5? We sure can. Oh, I should have put Y hat because this is a prediction equation. I would be putting in the 155.5 for the height. And we can make a prediction. Oh, I forgot. I was going to show you what that looks like if I press the graph button. There's that line. Now, me saying 70%, and that, see, not 70% of the points are touching it, but it's saying that the pattern is pretty strong of following that line. Okay. Anyway, so this ends up giving me a predicted weight of 21.4 kilograms. Now, just to review, interpreting the slope, this would mean for each increase in length, the weight is increasing by 1.68 kilograms. Now, what would the Y-intercept mean? It would mean if the bear is 0 centimeters long, it weighs negative 139. So the Y-intercept would not be a reasonable interpretation. Just kind of reviewing that. We're going to be talking about R squared in a little bit here, so we'll be coming back to that. I'll come back to it in a second. Let's go through a couple of more examples just to review. A school cafeteria has a salad bar that's priced based on weight, with salads costing 30 cents an ounce. Students fill a container that weighs 8 ounces when it is empty. Define X to be the weight of the filled container and Y to be the price. The relationship is listed here. Explain what it would mean if X is 8. That means that the weight is 8 ounces. Well, it says the empty container weighs 8 ounces. The empty container weighs 8 ounces. So that means the container is empty. Does the Y-intercept have a useful interpretation? Will the container ever weigh 0? No, this would be not useful. The weight will never be 0. What's the meaning of the slope? For each ounce increase in weight, the price increases by 0.30. So that's 0.30. If the container plus ingredients weighs 20 ounces, how much does the salad cost? So that would mean we're going to do an interpretation. We're going to do a prediction. So hopefully you've tried this already. I got 3.6, so that means it costs $3.60. Go ahead, and if you have not tried the next one, try it on your own. And then press play when you're ready to see the answers. The interpretation of the slope. For each increase in hand span, and you could say for each centimeter increase in hand span, the height increases by 0.7 inches. What is the estimated average height of a woman with a hand span of 20 centimeters? That's an X value. Now it tells me that Molly actually has a hand span of 20 centimeters and is 66.5 inches tall. What is the prediction error or the residual? The residual is the observed minus the predicted. So the observed is 66.5 minus 65.1, which is 1.4 inches. So that means Molly is taller than what is predicted, so Molly is above average. Now, the next thing I want to talk about is that R squared. That's the last thing we really need to talk about in this section. So consider that club speed versus distance example again. If we were asked to predict the distance of a randomly selected shot, what would be a good guess? Our best guess would be to take the average distance of all the shots taken. So we can use the sample data and get that. Now suppose we were told that this particular shot resulted from a swing of a club head of 103 miles per hour. Knowing that there's a linear relationship, we can estimate the distance of the shot by using that regression line, by plugging in. In statistical terms, we say that some of the variation in this versus this is explained by the linear relation in the speed and distance. The variation, proportion of variation in the response variable, or our Y variable, the proportion of variation in the response variable that is explained by the regression line is called the coefficient of determination. That's R squared. So R squared is always going to be between 0 and 1. It's telling me the percentage of the data that is explained, or the variation that is explained by the regression line. In other words, it measures how well the regression line describes the relationship. The closer it is to 1, the better the line that describes how changes in the explanatory variable affect the value of the response variable. So let's look at some data. Looking at these 3 sets of data, let's look at their scatter plots. I'm not going to make us do each one of these by hand, but if we look at the scatter plots, the first one, the regression line matches beautifully. In the next one, they're just a touch off. On the third one, they're very far off. Now, what ends up happening is that r squared on this one ends up being 0.9999. The r squared on the next one is 0.947. On the last one, it ends up being 0.094. So the way we interpret those r squared values is that on data A, 99.99% of the variability is explained by the regression line. On the second one, 94.7% of the variability is explained by the regression line. The last one, only 9.4% of the variability is explained by the regression line. So let's look back at that bear example. R squared was 0.483. So this means that only 48.3% of the variability is explained by the regression line. That's why this is called the coefficient of determination, coefficient of variation. Could we match up graphs with the coefficient of determination? Well, it's very similar to when we were doing R. The better the fit, the higher the R squared. So C would definitely be graph 4. Now notice that the direction doesn't matter. It's how closely it explains the data. So I would say 0.90 would be 2. Now which one shows the least amount of data fitting? That'd be 1. And then 3 would be A. Oh, I did the R squared one there. Oops. R squared was 0.483. And we already talked about that. That's 48.3% of the variability. Oh, I got ahead of myself. Is explained by the regression line. So is it a really good model? Maybe not. The correlation between height and weight is R equals 0.40 for 12th grade male respondents. There's 1,501 respondents in a survey done in 2003 by the U.S. Centers for Disease Control and Prevention as part of the Youth Risk Behavior Surveillance System. Calculate R squared. Well, that would be, we just take R and square it. So 0.4 squared. That's 0.16. Ooh, write a sentence that interprets this value in the context of this situation. So 16% of the variability in height is explained by the regression line. Now let's say those heights and weights were recorded in meters and kilograms. What would be the value of the correlation if the measurements had been done in inches and pounds instead? Would changing your units change the correlation? No.
it would be the same.